Hello. We have considered many issues about the linear regression model. We started from why we need a linear regression model and how we define the equation and what's the required assumptions and what's the interpretations. And then we learned how we estimate the parameters in the model, and then we can conduct some inference methods like calculating the confidence interval or calculating the standard error or calculating the goodness of fit like R squared or sum of squared errors or standard error of the regression. And then and then uh, in the last lecture, we learned how to interpret when the regressor is a binary variable, not a continuous variable. And also, we learned how to implement the linear regression model on Stata. So all of these tools are very important, super important anywhere, not only in like economics, but also in like literally anywhere. Statisticians and like any social sciences and like companies. So you are going to use these methods a lot of times in your career. So um, don't just take it too easy. It's seriously important. And what we are going to do today is a little more difficult in pronunciation. So the title of the title of this part is heteroskedasticity and homoskedasticity only standard errors. So basically you can feel that something is hetero something and homo something. Um, Heteroskedasticity, so skedasticity, I don't know where it's originated from, maybe Greek, Latin, I'm not so sure. But skedasticity is volatility. It's a volatility, dispersion, and spread. It means something like that. Like you can think it as a variance. So heteroskedasticity means the error term has different volatility or different variance over different groups. But homoskedasticity means the variance of the error term is constant across different groups. Like for example, when you think about the test scores and class size example, when you change the class size, is there any difference in the error term or are they the same? Uh, that's the main question. If they are the same, which is nice, and like we'll have like simpler formula later. So then we say the setup is homoskedasticity. The error term satisfies the homoskedasticity assumption. But in general, we are not sure about the homoskedasticity. So not assuming homoskedasticity means heteroskedasticity. So just heteroskedastic models are more general setup, and later we are going to we learn how to implement, how to accommodate a heteroskedastic a model in the OLS estimation, and especially how to calculate the standard error under each assumption. And as I said, like mathematically, you can write it this way. Think about variance of the error term given class size. X is class size and error term is the error term. And if this variance is constant across different values of x, then we say homoskedastic. Yep. And otherwise, if it's not constant, it is unrestricted. So if the variance is can take any form, then the error term is heteroskedastic. So the volatility can be different across different class size. So then, simply speaking, the problem is here. Think about the simplest possible case. Suppose that the class size is classified either small or large. So there are only two possible class sizes, and heteroscedasticity means small class size outcomes and the variance of the small class size schools and the variance from the large class size schools are different. Then we say the model is heteroscedastic. On the other hand, if the small class group and the large class group have the same variance of the error term, then we say it is homoscedastic. And the difference is actually what we want to calculate is the difference in test scores between these two groups. And after estimating the difference, we need to calculate the estimator's standard error, which measures the accuracy of your estimation. So then that standard error, the formula for that standard error depends on whether the variance is heteroscedastic or homoscedastic. As you can see, the formula in the first case, if they are unequal, then can be written this way. But if they are equal, then actually looks more complicated, but actually it's easier. So then the terms look very scary, but it doesn't do any harm. It's simple. The idea is very simple. In more general, homoscedasticity can be found from the picture. If you have a scatter plot, then homoscedasticity it means this dispersion. So dispersion at 15 and dispersion at 20 and dispersion at 25 must be the same in a homoscedasticity case. By the way, this picture is in the textbook as an example of homoscedasticity. But as you can, so the red arrow is added by me. That's what I added. But I don't think it picture shows a homoscedastic case, because when I first look at the picture, I thought this was an example of heteroscedasticity because this dispersion is smaller than this dispersion, and this is the largest dispersion. So I think it's clear the distribution becomes like so. Dispersion increases as the bell curve it becomes more flat and have longer tails. And clearly, I thought this bell curve has longer tails than this guy, but the textbook explains it is an example of homoscedasticity. I'm following the textbook, but I cannot agree with the textbook's interpretation. I think so. It's not clear. So the picture is not clearly homoscedastic or heteroscedastic. So if you compare this, and if you believe this distribution is more dispersed, has a larger variation, then that larger variation than this one, then that's heteroscedasticity. Anyhow, the point here is if you have the scatter plot, then you can approximately tell what's going on. And if the difference is clear, then it's clearly heteroscedasticity. So here is another example. It's a better example and more clear example. Think about years of education and earnings. So as you are more educated, your earnings will increase. Hourly earnings will increase. I don't know what this so these guys finished only elementary school, and 12 years. So it's years of education. So uh, elementary school, completion of elementary school, and 12 years completion of high school, and 16 years completion of college. And more than that is maybe master degree, something like that. So if you look at this scatter plot, it is clearly there is a higher variance here than here. So maybe like a high variance and becomes smaller, and then the variance increases again, right? And it is not unnatural. Somehow it's natural. So think about that. When you only have 12 years of education, so you have high school degree, you completed high school, then the 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 variance can be smaller because your like prospects are kind of limited. What you are going to do, like so, for example, like in more extreme, suppose that you only have say 7 years of education or 8 years of education. So you barely finished like middle school, say. Then because of the limited education, I think the the possible you cannot your selection of jobs is quite limited. So there is little variation within the middle school graduates. Anyhow, so they are going to do something like so they'll be in the similar jobs and making similar earnings. On the other hand, if you graduate a college, the ceiling is much higher. So the possible ceiling is much higher, but the flow is not that higher than the lower education cases. So you understand my point. Even if you get college degree, it does not guarantee you a higher salary, but you have to achieve higher earnings by additional effort, or you have to be smart enough or make enough efforts to get a higher salary. And when that is combined with college degree, you can go up to the higher salary. Otherwise, there are many people who do not use their college education at all on their job, right? So if you think that kind of mechanism, it's not that weird. So having heteroscedasticity is a little more natural in many examples like that. Okay, so graphically now compare this and this. So this is high school graduates, 12 years, and this is college graduates, 16 years. So if you compare them, clearly the dispersion is much higher here. So it's a clear example of heteroscedasticity. And this is class size data. Class size data look like this, and from here I think it's more like a homoscedasticity, because I think the band. So if you think about the trend line, the regression line, and the dispersion from the regression line is more like a uniform. It looks like a band, uniform band around the regression line. So you can imagine something like this. So the dispersion here and dispersion here are similar, like anywhere, no matter where you choose. It looks like the dispersion is similar across different values of student to teacher ratio. So in this case, I think it's a good example of homoscedasticity, which will make the formula much easier. But you don't need to worry about the formula, because Stata is going to calculate that for you, and just you can change the formula by writing one or two words. So don't worry about that. So then, so okay, I'm going to stop the video here, and we'll continue in the next one. See you in the next one.